Okay, hello everyone. This is the final subtopic on topic 5, controls, and starts off. We're going to talk about the design of controls here and some human factors principles. But I want to just kind of talk a little bit here on one slide with a major example, something that I have worked on in the last decade here. So this is, real life come to pass here. This is a picture of, actually, this is a rendering. I guess I couldn't find a good real life picture because this bridge is finished. But as this bridge was being constructed in 2015, 2016, there was an accident involving a construction worker, and his name was Jose Suarez, and Suarez, Jose passed away. And I worked as a human factors consultant in the wrongful death lawsuit, that was involved. Actually, there were several lawsuits, and I was working the angle that had to do with control confusion. So I was speaking basically from my from my scientific expertise about the need for controls to have haptic differentiation in addition to visual differentiation. You've heard me talk about this before, in the Alphonse Japanis experiment. So this was a real life accident, and essentially what happened was, Mr. Suarez was working on a barge in what we call I guess we call it a man lift, but basically like an elevated platform. And it's a vehicle, right? So it's one of these things where you can be in the control basket and this entire machine can move on wheels, or it can extend, to get a worker closer to a workspace. So if you're building a bridge, you're on floating barges on these machines. And, he was extended up and working on the bridge, applying, some rivets or something with the control units for the box he was in and the vehicle, the vehicle itself. These were the controls, and those were behind him because he's working right here on the bridge, and the controls are behind based on that orientation. And so very common practice would be to reach around behind and adjust your position relative to the workspace. And if you happen to touch one of these controllers and push it and the workspace gets closer to you, you think, okay, I've hit the right controller. But if that workspace gets closer to you because the entire vehicle is moving as opposed to just your basket, then that could be a problem. And in fact, long series of additional details I'm going to skip over, but what happened was the entire vehicle control got activated instead of just move my basket closer to the bridge. And so then the entire vehicle went off of the barge. It wasn't safe. The safety chain wasn't in place like it should be. That was another major issue. And Mr. Suarez was tethered for safety reasons. He was tethered to the work basket. And so when the vehicle went off the barge and went down to the bottom of the river, so did Mr. Suarez, and he, unfortunately passed away. So this was to me, a pretty clear-cut case of control confusion. And this is one of those where you could say, well, the human factors, you should turn around every time and look very carefully at which control you're operating. But I would say the nature of the work kind of required him to have his back to the controls, and the controls themselves could be modified to make this less likely to occur, right? So I'm going to talk about some of the potential ways, some potential concepts to think about in the design of controls. And foreshadowing, Genie, Genie is the manufacturer of this man lift, and they in fact did redesign their control box. So I'll show you a picture of the redesign. Not necessarily because of anything I did, but just coinciding kind of with this accident, I think. Maybe here's what I'll do. I'll post this scientific report because it's a public record thing. I'll post that on Canvas. So if you want to read more about it, you're welcome to. All right. Good. So textbook sorts of feedback now here. So actually, for your assignment for this topic, it actually ties into the topic 4 with displays. And displays, I ask you to go through the 13 display design principles. For the controls aspects of what I'll ask you to do, these are the 3 basic criteria points you're going to think about and evaluate. Okay, so the accessibility of a control, the identifiability of the control, usability of the control. So we'll talk about each of those. All right, so for accessibility, I got to be able to reach the control with my human body, right? My human appendages. And so anthropometry, this is a topic coming in the second half of the semester about the physical, measuring the physical dimensions of human limbs and hands and things that will operate controls. So we need to know what, the sizes of these appendages and the clearances that are required to operate controls biomechanically with human limbs, right? Okay, the location of a control matters relative to the work space or the display area. And so, that needs to be considered. And you need separation between controls so you don't accidentally bump one when you're going for another one, right? All right, so here's a standard here, and this is a little dated now, but it's still, it's still valid. But to look at your average, I should say average. It's a tough thing to say the average human, but we have design standards based on average sizes of various dimensions. So if we have push buttons, then the design standard here, we need at least 20 millimeters between those buttons so that if I hit one, I'm not inadvertently hitting another one with my fat finger. And optimally, it's 50 millimeters. Toggle switches, levers, hand wheels, etc. We have different minimum and optimal separations among those controls. Now that matters a lot when you have a control space that's extremely limited in land space, right? In real estate, and you have a whole bunch of controls that you need to have individually, that you can interact with individually. So we need to have these separations. It's a critical thing, but it's also our limiting factor here in terms of how many physical controls can we put in a space. Okay, so that was accessibility, right? Got the soundboard back, so yeah. Okay, so identifiability. Now we get to talk about the Alphonse Japanis stuff again and about the Suarez case and the accident there, right? And so first of all, we need to know what that control does visually. We need to be able to read a label or see icons associated with that control, so we know how it's labeled. Tactile and haptic identifiability. I've now given you several examples of why that's important. The control should also tell the human about what it does. Okay, so we don't want to be too confused. I wonder what happens if I push this joystick. I should have some sort of I should have some sort of clue, and we'll talk about what that term will be here in a minute, that tells me how the humans should interact with it. And also, I want to know the state of the control. I want to know, is that thing in, an on position or an off position, an active position or inactive, or, what's going on with the state of the system that is conveyed through the current state of the control. And remember in the, I guess, 5.2, we talk about the difference between push buttons and toggle switches. And toggle switches, one of their key things is that they communicate their state by the position of the switch. So you can actually look at it and see, okay, that light switch is flipped on, for example. That is a good example. There, light switch, yes. Communicates the state of the control. So again, I can obviously look around a room and be like, the light's on or the light is off, but it is also nice to know, hey, the power is going through that circuit or it's not. And that would be the state of this toggle switch. All right, so actually, here's my counter example, actually, right? So if I've got this, I can say, okay, well, it's in the down position, but I don't necessarily know if that is like how this represents the state of the electrical system. Is this opening the circuit or closing the circuit, right? And so these are examples of, well, maybe we can have, some clearer indications of the state of the system. We have actual illumination on this panel when the power is being applied, or I can have that little green light turn on when the circuit is live. So it gives me, I can see the rocker position, but then I also have a redundant clue that's telling me here's the state of the control. Okay, we talked at length about color coding in the displays lecture and other ways that you can make controls look like they go with a certain part of the system, like a display. Labeling can help there. And then finding, ways, proximity compatibility principle, anybody, right? To make a control look like it goes with a display element. And there are many ways to do that. These are several examples. Make them similar shape, color, size, put them in a general proximity to each other, have them operate in the same, in a mapping way, the direction of motion. So, and now we've talked about this a few times, but the example of having different hand controls not only look, but feel quite different. So I don't need my visual attention to tell I've got the slats or the flaps and not the, not the throttle in my hand right now. So yes, again, shape and color, it's a redundant encoding. And we've seen this picture before. I can't remember if I've showed you this one before, but this is an example of a nuclear power plant where you can imagine somebody is needing to operate multiple different controls, and it's beneficial if they don't always have to look down to visually distinguish, am I doing the right valve or the left valve? And so, as it conveniently, if we are having a beverage sorts of labels on taps, those will screw right in and they can serve as a control handle just as well as, as the factory standard. And these feel very different and look very different, so they can be really more effective for differentiation. I mentioned that Genie did redesign their controls, and so the main difference here is they no longer have the previous. Here, actually, I can show you. So the original, the accident one, this is literally the one they pulled out of the river, had 3 controls and all identical knobs or basically handles on those joysticks. And the redesigned one, they removed the middle one, which, again, proximity compatibility, it shouldn't be close if you shouldn't be using it. And they made just 2 of these, and then they made one taller, so it feels distinctly different, even if I'm wearing heavy work gloves. That's another thing to think about, right? So, if you had made, you have to have probably a fairly substantial difference, not on this level, but more on this level if I'm wearing big, heavy gloves. Okay, so still on the concept of identifiability, realize that you might really work a long time on some really informative, iconic labeling, and then consider that, well, when you're activating the control, can I still see the labeling? And this is an example of, well, maybe not, right? So if I'm reaching and I'm trying to adjust my lights here, and I have to, change my perspective, move my hand away in order to read what I'm doing, then that's not as effective as if I knew what I was doing while I was interacting with it. Here's my pet peeve example. So I've got several TVs in my house, and I tend to watch them with the lights off if I can help it, because I know as a human factors person, that is a better visual experience. Problem is, with the lights off, this limits my visibility of my main controller, which is a TV remote. And if you have an older TV, like some of mine are, or at least an older TV remote, this can be a real challenge if I can't look really clearly to see, all right, where's the button 8? I got to go to channel 8, right? So I'm going to feel, and I'm maybe going to have to count rows or something. It's going to be a very confusable interaction, and especially if the lights are off and I can't see these labels. So think about that and compare that then with a lot more, modern sorts of controllers. And maybe you'll notice this yourselves, but a lot of more recent controllers do a much better job of having different shapes, haptically differentiable controls. So I can feel, all right, I'm on the right control instead of having to look at it to be sure. Now, it's not going to work for everything, but it is going to be considerably better than, a uniform sort of feeling button interface like this. Okay, so now accessibility, identifiability, and our third step here is usability. And a big part of this is, as a human, if I walk up to this complex control system and I just use my intuition and start messing with the thing, how closely is my intuition going to match what actually happens? And if it does, this is what we would call a maximally usable system. It is, there's transparency between my intention as a human interacting with the control and what happens in the system. Okay, so this is a term that came up, I want to say in the first lecture, or the first few topics, or the first, topic 0, topic 1, this concept of affordances. And this, I remember we defined this before because I showed you a few examples of door handles that are poorly matched as far as the affordances go, because they don't fully communicate what you're supposed to do, or they actually communicate the opposite of what you're supposed to do. So a door handle, when I approach a door, to me, if I've never interacted with that door before, a handle communicates grab and pull. Of course, this guy isn't me, also didn't read the sign, but in general, this says pull. And I gave a few examples of doors you actually need to push, but they tell the human, hey, I'm a pull door, because they have that handle facing the human. So this is an example of an affordance. The affordance of this handle is grab and pull. The affordances communicated by buttons are push, right? I can look at, here we go, my soundboard, right? I can look at these and I can see that those are buttons. Sorry, I unplugged it so it didn't make the sound. But those buttons, I don't have to think too much to determine how do I interact with that control. It is a button. It communicates buttonness. It says push me to the human. There we go. All right, there we go. So the actual definition I want you to make sure you know well is the perceived and the actual properties of a thing that a human interacts with. These are usually visually communicated because I'm approaching the control, and before I touch it, I only have my visual input for what it's going to do. And these are basically the clues that I have for how to interact with the thing. If I approach this system, I have a pretty reasonable guess. I mean, this is just a picture from online. I don't really know this, but I have a pretty reasonable guess that I could grab and twist those controls right there. And it's not, for example, something that I need to pull or push a button or do something, different than, I hope you agree with me, if you were going to try to turn on water with this sort of an interface, you'd probably grab and turn. Now, let me just add a really quick, yeah, but though, because if we're thinking about the example of the door handle, yeah, I can see that that's grab and pull, but wait, I'm not exactly sure because I've had enough experience to know sometimes it's grab and push. So it's not exactly 100% telling me what I need to do in this case. And in this case, I'd look at this and say, I bet that's a grab and twist, but I'm not exactly sure which way I need to twist it. So one additional thing I may have to, do trial and error to find out. Compare that with this sort of a control. You might say, okay, well, I'm still mapping, I assume hot and cold based on my cultural sorts of, expectations. And I can look at this and say, yeah, I have a pretty good idea about not only what to do to turn the thing, but which direction to turn it. And then it gets even more complex. How do I adjust the flow of the water as well as the temperature when I have these controls versus this 2-in-1, this kind of combined control, sort of a faucet control there. So just things to think about, because all of these are cognitive steps that a human potentially has to walk through between I've got an intention for how I want to use that control and then to successfully achieve that intention. Okay, so I've already said a few of these buttons are for pressing. They tell a human, hey, press me. Handles are for pulling. Plates are for pushing. And so all of these, we say these are the affordances, the physical properties, the visually perceived physical properties of the controls that tell me, that give the human clues for how to interact with it. And when those match my expectations, that's a sign of a good, an intuitive, a usable, high usability design. Yep. So that's okay. Good. Now, related to this as well. So, okay, I'm approaching. I've got the affordances. What do I do? Got my hands on the handles. I know what to do now. Now I'm providing that control input. I'm turning the handles. I'm pushing the joysticks. And now what happens in the system in response to these interactions, the mapping between my expectations and what actually happens is also part of the usability here. So I guess what I was just talking about there is the movement compatibility. If I push forward on the joystick, I expect the system to move. I have a certain expectation for how I think the system should change, right? And so those should be congruent, and they're not always. And sometimes you have systems that are designed based on, you know, an electrical or a mechanical aspect of the system, and the convenience of, you know, of certain shapes and configurations don't necessarily take the human's expectations as their first priority. Good. So yeah, the movement compatibility, when I move a control, interact with a certain dimension, I expect a certain outcome, and hopefully that matches, that should be compatible. Location also, this is kind of like proximity compatibility principle. It's also kind of like the principle pictorial realism, you know, making like that's the one where it's the temperature is higher when it's up and lower when it's down, that you know, orienting the thermometer. And then the movement compatibility is very similar to the principle of the moving part, which is, hey, when a display element is changing, it should map what you expect in the change in the system. So it's kind of the control side of those two mental model display principles. There you go. All right, so good example here. I like this. I'm gonna have to draw a little bit. Okay, give me my. Great. So these are remote control cars. I assume everybody's had some life experience with one of these toys in the past. They're great. Now think about each of them. So if you can look at each of these controls, notice they are quite different in terms of, you know, how I would interact with these vehicles, but assume all of them can be used to drive this car around all kinds of, you know, forward and back, turn it around, have it come back at me, all of that. Now imagine I've got me standing right here. Here I am. And I've got my controller. And here's my car. And imagine it's got to go on a track out away from me, and then it's going to turn around and come back. And it's going to be in a loop like this. Okay. So I'm going to stand right here the whole time. And I'm going to have the car drive away from me, turn left, drive towards me, turn left. Okay. Now, keep in mind my human perspective and what I'm dealing with in the system. And now think about how you would manipulate each of these controllers in order to get that done. And if you don't know what's going on with this one, I'll cut to the chase and tell you this is the one I think has the best mapping in terms of my control mapping, my movement mapping, because so if I got this control, I basically got to push up, right? This one's got to go up to make it go forward. But the other thing is I got to push also up to make it come closer to me when it's on the other, when it's on the back nine, or, you know, it's coming back on the other side of that lap, right? So I've inverted that mapping when the vehicle is turned around and coming back towards me. Also, I want it to turn left here, but from my human perspective, it is moving from the left to the right side of my field of view, as opposed to from the right to the left. So I got to move this way to make, from my perspective, the vehicle shift in towards the right. Okay, so it's again a flip, you know, a mismatch there. I don't even want to talk about how weird this one would be, but it'd be a similar mapping. Now, what goes on with this here, this is pretty nice, because you essentially have a trigger which corresponds to basically a throttle on a car. So it's like pushing down the gas pedal is pulling this trigger. Maps very naturally to how I think about how vehicles go. But even as a child, before I was, had a driver's license and all that, if you think about, that's the just go button. That's the make the car go button. Okay. Very intuitive. I press the button, it goes faster. I let go, it stops going. Okay. And it goes forward. It goes according to the vehicle, it goes, in the drive direction. Now I can turn this is my steering wheel. And the cool thing about this, I can turn it to the left or to the right. And if I turn it to the left, the vehicle is going to go left. And that's going to be the case whether the vehicle is going away from me or coming back towards me. So think about this. The vehicle's coming back towards me. I am turning it in the same counterclockwise direction to get it to come around that turn there. So this controller, and I'm comparing it to these other ones, this controller, I would say, gives the most consistent control input and response compatibility. So there isn't an orientation of the human and the system where this would become a mismatch. All right. Back to mouse. Man, that was good, wasn't it? All right. Okay, so a couple of other, so we've now gone through the textbook's three major accessibility, identifiability, usability. A couple of other notes here. So on Canvas, we have, this is the Society of Automotive Engineers, and they have a standard, so for, hey, vehicles and controlling surface vehicles, these are what people most these are the standards so that we have a consistency with how people can anticipate certain types of controls to respond. So just a few examples here. If I want something to turn on, I want my car to turn on, the directions of controls should be up, not down, right, not left, and it depends on all these different types of controls, right? Forward, not backward, clockwise, not counterclockwise. And then similarly, right, so for off, it's the opposites. So think about things like I'm going to turn my car on, and I've got my key ignition, and I turn it clockwise, right? So that makes sense. It does, that mapping has been defined. This is the standard that says keep doing it that way, so people don't, have this inversion of their expectations. There you go. Okay, so it's just some of those standards, and then this is more detail is in the full document on Canvas. Cool. All right. So I talk about this a lot more in 631 in case anybody wants to learn more about that. But the idea of natural mapping between controls and the system you're controlling is a big topic, and it's something I have a lot of great examples about this. But let me just kind of point out one classic here. So the scientist Donald Norman, and he's somebody that has written a lot of books in our domain. This actually comes from one of his books, but he's kind of the master of this concept. He has a lot of good examples that go around this concept. So this may look, somewhat familiar to you, especially if you have spent some time around, older campus buildings or public buildings. You have this kind of a light switch panel. And a lot of times these light switches, they just, you may have a really hard time figuring out, okay, well, which light switch is the one that's above the meeting table? That's the one I want to turn on. Solution right now is to go and start flipping switches and find out, right? Now, I may take a guess and say, okay, well, looks like there's a light over there by the door, and so maybe this one is the door switch, and then let's try this one above the table. Trial and error, and maybe you get it, maybe you don't. But the point is, I don't have a confident linkage between each of these controls and the specific lights or the specific electrical circuits they control. So Donald Norman and his lab, actually, just to give an example here, said, well, this isn't going to work in our lab, so let's actually redesign that light switch controller. And so what they have here are toggle switches. These are also toggle switches, but we have toggles here. And on a top-down mapping of our lab space, let's just put the labels, or let's put the switches right above the lights they represent, very naturally associating a switch with a certain light in that room. This also comes from Norman, and just some examples of how when you have strong control mapping or natural control mapping, you need less and less sort of clarifying labels. Okay, so if we start in the top left here, I hope you'll take a minute and look at this and see that it's a kind of a ridiculous way to do it, and counterintuitive. So this one goes with that controller, this one goes with that controller. Maybe this is, you can imagine the designers of this is like a stovetop, right? You can imagine the designers were thinking, well, we've got the two large elements, let's have those be grouped together. Okay, that makes sense. And the two small ones be grouped together. Kinda, right? So some logic there. But I hope you'll understand that, hey, if I want to turn on the flame on this one to start cooking my macaroni and cheese, I want to know, without having to read labels too closely, that I confidently turned on the switch I intended to, or I intended to operate this part of the subsystem, right? Okay, so this one maybe does a little better. Now, I don't have as much labeled, but I don't need to, as long as you can assume proximity compatibility, right? That these controls go with these system elements, because they are spatially grouped in that way. So it's a way that intuitively the humans will associate these two with those and those two with those. If you disagree with me, please let me know why. I'm sure there are exceptions to that. I still have to look at this and think about, though, am I in the back or the front? And these are not mapped in a natural way. So I still have to look at those labels. Go down here and we say, okay, well, here's a couple examples that are better. And they're better. We know they're better because we don't need the labels and we can get pretty good guesses. But let's just assume, I can imagine a case where I put my macaroni on this burner and I have a flub, or I don't think that clearly. And I think, okay, well, here's the nearest knob to this controller. Maybe that'll do it. And I assume it's mapped this way, and the controls map in a similar square layout, but I don't know. And then similarly here, you can assume that these go together, but hopefully they do, in which case you would say, hey, this is a nice intuitive natural control mapping. But again, the clue here that it's not a good mapping, or it's not as natural as it could be, is we've got to have excessive labeling to associate that. So we can be more clever in the way we design the orientation of our controls relative to the system elements so that they more naturally go together. Another good example I like to bring up and think about, and we would talk about this if we were in person, are seat controls, right? Seat adjustment controls. And to think about aspects like, if I move it this way, will it move in a direction that I think is intuitive? And some of you are going to say, oh yeah, I've got this sort of control in my car and it's really easy and straightforward. But I would look at this and say, I'm not sure. I'm going to have to do some trial and error to figure out how this affects, the seat orientation. This is more similar to what it looks like in my car currently. And I would argue these are really nicely mapped, because it's kind of like I'm grabbing a seat pan or I'm grabbing the back of the chair and I'm moving them in a way that directly corresponds with movement of those parts of the chair. But of course, there's several different, models here. I may even have this, in a location that isn't on the chair. And to think about, well, how naturally do all of these, map to your intended change in the system? So there's not one good answer here, but all of these are different ways of interacting. And if you can think about how many mental steps do I need to make between, here's my intention for the system change, I'm going to give this a shot with that controller, which its affordances are telling me what I can do with it, and how closely am I getting to my intention with basically my intuition, or additionally, how many steps do I have to jump through? How do I adjust the seat pan again? Any of that is a sign of there's potentially better mapping between the control and the system that it represents. Okay, so still on the topic of usability. All right, so feedback from the system, through the control is essential. And I'm talking about two types of feedback. So when we make a control input, it's generally towards, I want a certain change in the system to occur. And then we need to check and see if we did achieve that state. Okay, so first I need to know, did the system receive my control input? Okay, so I'm typing a text message. Did my phone receive my, like, did my phone register that I actually pushed it? Or is it like, you know, the screen is off and I'm not looking at it? Or, oh, I missed it and I didn't quite get the letter I intended, for example. So that's the control input. But then also you can assume, like, if it's a larger system control, we would expect to see that in the system. All right. So if I, you know, if I push the joystick this way, I expect to see some movement of a vehicle or whatever I'm controlling that maps to that. And if I can see it, that's my feedback that yes, my control input was accepted and is moving me closer to my goal. So I need both the controller to tell me your control input has been received, and I need the system to show me that from my control input, the system is changing in the way that I intended. All right. Now, where this gets goofy is when some of that feedback is not present and people are having to, you know, they have less satisfaction in that interaction. They have less confidence that, you know, the message is going through. And then if we have delays in any of that feedback, this is where there's some interesting, you know, human factors sorts of implications. So 100 milliseconds is about, I've tried this before. I've got a Raspberry Pi that I can run old video games on it. So like all the games of my childhood. And I read enough to know, okay, well, here's the key limiting factor. It's the lag between your control input and what you see on the screen. And here are all these factors you can do in the way that you know, set up the emulators to minimize that. And basically at about 100 milliseconds, that's the key difference between me enjoying playing Mario Brothers or it being just a disaster, right? So being able to press the button to run to the right, if the delay is 100 milliseconds, that is enough to completely break the game for me. So you know, there is a limit there. But what's interesting is the nature of the control has a lot to do with how much delays will impact it. Okay, so when we say higher order controllers, I'm going to show you here in a minute, but we have okay, let me just show you. So as with higher order controllers, which I'm going to introduce in a minute, this response lag or any sort of delay becomes increasingly costly. So the higher order the control, the more that delays are costly to performance. And this is what I'm talking about with control order. So position control, and a mouse is a great example of this. I move the state of the mouse and the position of the represented system changes in a mapping way. The green mouse pointer there moves in a way that very naturally matches to my hand position, but the movement of my control changes the position of the system. Okay, so we'll call it position control, zero order. Contrast that with velocity control, first order. So now, if I push this joystick to the left or the right, you know, for most games where you would use that joystick, the velocity of the character you're controlling or whatever will move according to how far this deviates. Now compare this with the position control, okay? So if I'm playing Mario Kart and I push to the left here, that changes the orientation of my car and it makes it go with a certain velocity laterally to the left or right. It's not a position thing. So if I push, hey, I'm going to go a little bit to the left and my car starts going this way and I let go, it doesn't snap back to the original position. So it's not a position change. It is a velocity change, right? And also recognize here, so I don't know if any of you have experience with, you know, the gesture control. This is the greatest joy for Mario Kart for me. But turning that wheel is also a velocity control. So I'm changing the position of the control, but I'm affecting the velocity in terms of the speed at which I move laterally in this game. Okay, so again, velocity control, first order. Take the derivative of that, and now we have acceleration control. So the example here would be a throttle and a brake system. I apply more, if I change the state of this control, it affects the acceleration or a second order of control within my system. So again, lag, our big principle here, lag is inevitable in a system, but it is much less damaging. It's much easier for a human to overcome with these lower order sorts of controls. If I've got a lag in my mouse of 100 milliseconds, that's actually, I mean, it might be a little annoying, but it is not going to wreck my game. Okay. Assuming that it's a first order position. If you have a delay and you're talking acceleration control, now this could get very, very unstable very quickly. And you can imagine, slamming on the gas, nothing happens. Oh, and then it accelerates way heavy, but you've already stepped on the brake. And, so you can imagine that it'd be very difficult to control your intended speed, or your intended position, speed, or acceleration when you have lags in these higher order system controls. There we go. So with higher order, it is harder for humans to keep track of of where they want to be and maintain that position. And so we want to minimize these if we can help it. Humans are just generally better in working with lower order controls if those map to the task effectively. Okay, so last slide here, I think. Yep. Joysticks are a very common controller, both in industrial contexts, workplaces, but also just in our everyday lives. We play video games with them. We interact with all kinds of devices around our lives through what are effectively joysticks. So I have three different specific types of joystick I want to highlight here. The isotonic joystick looks like this, and if you can imagine that that stick there, it is very effective for a position control, because you essentially move it and it stays where you move it. So it's a persistent control. It doesn't snap back to the center, right? And so, hey, if I want to move, I can actually use a joystick like this to orient my mouse pointer around this two-dimensional space, very nicely mapping, because then again, I can see the state of the control, and it would map to the state of the system, where my mouse pointer is. Not great for a higher order sort of control. So if I was going to use this to impact the amount of acceleration that I have in my Mario Kart game, this would not be a very effective one, because I would have a very hard time getting a nice stable acceleration, or where I want to be. Okay, so that's an isotonic. So this is no force feedback, or there's no the force input isn't there. It's the position that matters. And then the opposite of that is an isometric joystick. I don't know if you knew this, but if you've got one of these things on your computer and you always bump it and you're like, what the heck is that? This is an isometric joystick, and it's isometric because it doesn't physically move, but you apply pressures, you apply forces onto it, and it reacts to the force vectors. Okay, this is great for higher order control. Okay, so here you go. I'd like to ask that sort of question: high order, low order, which ones are going to be better joysticks? But you can also think, like, if I'm trying to get a nice position pointer, if you've ever tried to, now I want to get my mouse just right over there, and you've tried to use this sort of a joystick, it's not as naturally mapping to me. I don't like it. It's much more effective to have a position zero order controller. Good. And then the best of both worlds, this spring-loaded version of a joystick. This would be one where, yeah, you could have it represent position, but you also have the spring centering here. So this would work very much like a one of these control sticks, where it'll snap back into a position. So if you are entering in velocity changes or acceleration changes, you've got that 0 point, so you can always kind of it'll help you with the stability of the system. Generally, a most preferred one there. Okay, so that's it on controls. Tune in next time.